Right, hello everybody. This is another supplemental video to my series on heteroskedasticity and Harmless regression. This video deals with the case where we have many different variables, so it uses matrix notation. I also uploaded another supplemental video which deals with the case of OLS regression with one variable and one constant to derive the formula of heteroskedasticity, which is a bit more interpretable. This video, as I said, derives the variance of the OLS regresses under heteroskedasticity in matrix notation. Enjoy!
Alright, I'll start again with the linear model. So now we've got y is equal to x beta plus epsilon, where x is a matrix and y, beta, and epsilon are vectors. And then we've got the normal OLS estimator, that is beta hat is equal to x prime x inverse x prime y. Short note notation, I'm using primes here, or dashes to denote the transpose of a matrix. Other textbooks often use a capital T, or also use a dash. This is just a matter of notation, just so you're aware. Okay, now we plug in our data generating process as usual for the y. So we get that beta hat is equal to x prime x inverse x prime x beta plus x prime x inverse x prime epsilon. Now here we multiply a matrix with its inverse, so this is the identity matrix. So now we can rearrange, and we get beta hat is equal, beta hat minus beta is equal to the x prime x inverse x prime epsilon. So this is essentially the deviation between our beta hat and our true beta. All right, so the variance of beta hat given x, so this is the conditional variance, is equal to the conditional variance of beta hat minus beta. I mean, beta is just a constant, so it would drop out of the normal variance. Doesn't matter for us, given x. And now we can use our useful expression here and substitute it. All right? So, and then we've got the quadratic form for the variance. Let's do it here. The expected value of beta hat minus beta hat minus beta prime given x. So this is the quadratic form for variance in matrix notation. Then we can plug in what we had here. So we get the expected value of x prime x inverse x prime epsilon prime x prime x inverse, conditional on x. Okay, we've conditioned on x, so we can move everything that includes x out of the expectation. So this gives us x prime x inverse x prime, this thing, expectation of epsilon prime given x prime x inverse. Now this is the covariance matrix of epsilon conditional on X. So essentially, along the diagonal, how does it look? Essentially, we've got a big matrix, and here we've got entries on the diagonal. Those are the conditional variances, and we've got off-diagonal entries. These are the conditional covariances between different epsilons, epsilon i's. So essentially, those capture whether errors are correlated. So one case that you often find where errors are correlated is if you observe the same person over time, then probably the errors will be correlated over time for that person. So that's the case you encounter in panel data or in time series data. Okay, and this matrix we just define, because we feel like it, as omega times sigma squared epsilon, in fact. This is just a normalization. The sigma squared epsilon is the unconditional variance. So sigma squared epsilon is equal to the variance of epsilon unconditionally. That's just a normalization in the sense that it just scales the omega matrix. I mean, you can multiply or divide a matrix by 5 and pull out a 5 in front of the matrix. That doesn't really change too much. All right, so what we get is that the variance of beta hat conditional on X is equal to X prime X inverse X prime omega X X prime X inverse times sigma squared epsilon. So this is a scalar. Right? Now, there's the spherical error assumption for homoscedasticity and no autocorrelation. And this assumption states that omega is equal to the identity matrix. That's for homoscedasticity and no autocorrelation. So if that's the case, then we'd have no omega here, then we'd have X prime X inverse, X prime X inverse. One of those would cancel out and multiply with sigma squared epsilon, and that gives the variance of our beta hat in the case of homoscedasticity. But the general form includes this omega term, and that's something we need to estimate. Now, we can make multiple assumptions on omega. The simplest, which you do for the cross-sectional case, that you assume that there's that there's no autocorrelation, but you assume that errors are not homoscedastic. That's essentially the case for the robust standard errors. Now we just need something that estimates this matrix. And what dimension does this matrix have? X prime omega x. X prime is a k by n matrix. Omega is an n by n matrix. X is an n by k matrix. So the dimension of this thing is a k by k square matrix, where k is the number of coefficients we've got, so the length of beta, so to say. And there are 3 different ways to do that. They're known as, I'm trying to move that, yeah. They're known as HZ0 to HC3. HC0 and HC1 are relatively straightforward. HC2 and HC3 are a bit more tricky to interpret, but we don't worry about this here. If you're interested in it, give me a shout and I might produce a video on the different types of robust standard errors in the future. What's important to know is that HC3 is generally has the best properties of these estimators, so HC3 gets a little hard because it does the best job. Well done, HC3.
Right, I hope you enjoyed this supplementary video and have a better understanding of heteroskedasticity more or less now. Check out the rest of the videos on my channel for the other videos on heteroskedasticity and more or less regression, as well as for other topics in causal inference. Thank you for watching. I'd appreciate a like and subscribe. Bye.